Today we're going to be talking about Riemann sums, the topic of section 5.1. There's 5 sections in chapter 5 that we're going to be covering over the next couple weeks. And I want you to keep in mind the common theme between each of the sections. We're going to learn, first of all, how to approximate the area under a curve. Then we're going to find out a little bit later on how to find the exact area under a curve. And then we'll apply that to other types of functions. But the bottom line is, the common theme between all 5 of these sections is that we're trying to use calculus to find the area between a curve and the horizontal axis. That's it. So an entire chapter devoted to learning about area between the curve and the horizontal axis. So we're going to keep that in mind, and we're going to focus on today 3 goals. And the 3 goals are, number 1 would be to approximate the area. Approximate the area. And when I say the area, I mean the area between the curve and the horizontal axis. For example, all this stuff here. Okay, so that's the area. That's the exact area, if we could figure out that number, and you'll learn how to do that later on. But approximating the area, we're going to be using initially, we're going to be using rectangles, approximating area. So we're just going to build a bunch of rectangles, and you'll learn how to do that as well. And if you can figure out that, if you can figure out what the areas of each of the rectangles are, then you will have learned how to approximate the area. And then the next goal for today is to interpret what that approximate area means. So in terms of a kind of a real-life type problem, in context, the area between the curve and the horizontal axis isn't always going to mean the same thing, but nevertheless, again, that's the common theme, is to find that area. And then the third goal is to understand whether or not that area, if you have an overestimate. So in other words, we're going to be estimating the area here today. Overestimate or an underestimate. Okay. So if you can be thinking about those things while we work through each of the problems, then we're good to go. Now, if you look at the current situation of all of these 5 rectangles underneath the curve, you could hopefully clearly see, if you understand that the curve or that the rectangles are on or under the curve the whole way, then we can see that we have an underestimate for the current situation. And then we could see, if we build rectangles above, let's say up here, we have rectangles above like that, where every rectangle is on or above the curve, then we would see we have an overestimate. So we're going to be dealing with each of those situations, and let's go ahead and get started with an example. Okay, so example number 1, relating it to real life. Let's suppose that you're traveling at a rate of, let's say you have an average speed. Let's put the EX right here for example. Average speed of, let's say, 30 miles per hour, and you travel at that average speed for 2 hours. Okay, so way back when you learned that rate times time is equal to distance, and then the question would be, how far have you gone? How far did you go? Well, pretty clear. If your rate is 30 miles per hour, and you multiply that by the time that you've been traveling, 2 hours, you get 60. Okay, so that's your distance traveled. But here's another way to kind of look at that. Let's include the units of measure. 30 miles, this will be really helpful if you get this. 30 miles per hour, and you travel for 2 hours. Well, just like you can cancel fractions, you can cancel these units of measure. You can cancel the hours and take a look at what happens. If you go 30 miles in 1 hour, then you go for 2 hours, you cancel the hours and you get 60 miles. Okay, so you've traveled 60 miles. Alright, well, let's take that same example and let's draw a picture of it. Draw a picture of it. Let's say the horizontal axis is t and time, t meaning time, and the time is in hours. Okay, and then the vertical axis is the velocity. We can call it v of t, and that would be in miles per hour. And we can actually, like I said, we can graph that situation that we just talked about, in which the velocity throughout the first 2 hours was 30 miles per hour, and we went 2 hours. Okay, so if we went 2 hours at 30 miles an hour, the speed or the velocity was constant. Now, the velocity being positive, that would be indicating that the speed was positive. Speed always has to be positive, but I mean, we're going forward or to the right or up or whatever. But the 30 being velocity is a positive number in this case. So remember what we were trying to find. We were trying to find the total distance traveled. Okay, so write this stuff down. This is kind of a cool thing here. So the total distance traveled, if we take a kind of a brief break here and we say, well, what's the area of this rectangle? The area is 30 miles per hour times 2 hours. Well, if the area is 2 times 30, then the area is 60. Okay, so the area is 60, and the 60 would represent the miles. So let's just take a step back here and take a look. The total distance is equal to the area under the curve. Under the curve. Now, mind you, later on you'll learn that you'll be able to find the total distance as long as the area, as long as the curve is totally above the t-axis over the entire interval. So we'll deal with that later when the curve goes below the t-axis, but for right now, area under the curve, as long as the curve is above the t-axis, represents the total distance that whatever traveled in that amount of time. Okay, so that's pretty amazing that distance is equal to area. Think about that. Distance and area are the same thing in terms of this context, and let's apply that to another problem. Okay, so let's actually do some calculus here with Riemann sums. So this is our next example. So what we want to do is we want to find the area. We'll get back to the velocity part here, but what we're going to do is we're going to find the area under the curve. Let's let this be y equals x squared plus 1. So we're going to approximate the area between x equals 0 and x equals 2. Okay, and so the horizontal axis is our x, vertical axis is our y, and we have the curve y equals x squared plus 1. Okay, well, let's plot a couple points here on the curve. Here, this point here has the coordinates 1, comma. Now the height here, height right there, depends on x. Okay, so if x is 1, then the height would be 1 squared plus 1. 1 squared plus 1. So the coordinates of this point right here are 1, comma, 1 squared is 1, 1 plus 1 is 2. So the coordinates of this point are 1, 2. Okay, well, let's do another one. Let's go right up here to this point, and let's list the coordinates of that point. So the x coordinate is 2, and the y coordinate of this point would be what? Well, if the point is on the curve, and the curve represents the picture of all the inputs and outputs. So if the input is 2, the output is 2 squared plus 1. We have to follow the rule. 2 squared plus 1, and so we get 2 comma 2 squared is 4, 4 plus 1 is 5. So we get the coordinates of that point, which are 2 comma 5. Okay, well, that's all fine, but remember our goal number 1 is to find the area, approximate the area under the curve, and let's also pick one more point. Sorry, I meant to do this one over here. So this point right here has coordinates 0, comma, and I think we can do this verbally here. 0 squared plus 1 is 1. So we have the point 0, 1, which is on the curve. Okay. Well, now it's time to approximate the area under the curve using rectangles, and we're going to draw a couple rectangles here. We're going to draw one. What color should I use here? Let's use this color here. Okay, so we're going to draw one rectangle using, or the base of the rectangle being the space here between 0 and 1. So the base, and then we go up to hit the curve up on the left side till we hit the curve, and then we're just going to, that's not a great approximation, but it's all we've got right now. And then we're going to use another interval here from 1 to 2 and go up from the left side of that interval till we hit the curve, and then we're going to build another rectangle. Okay. Now there's all different ways to do this. In other words, there's lots of different ways that you can build your rectangles. You can build more rectangles if you want, but just the basic concept is you're going to draw a finite number of rectangles, and you're going to add up their areas to find the approximate area under the curve. Now we can see that there's a space here. That space right there, we realize that we're not coming up with a very good approximation, but nevertheless, we'll get to the good approximations later. Let's just go ahead and understand we're coming up with an approximation. Okay, so then the area of this rectangle, okay, area of this one would be the length of the base times the width, or base times height, however you want to say it. It's the length times the width, base times height. Okay, and we know the dimensions of rectangle, we just multiply the width times the height, whatever you want to say it. Okay, so base times height, I guess I'll use those words, and we can see that the base has a length of 1. Okay, and the height, we already said that the y coordinate of that point right there was 1, so we know that this length here, the height I should say, is 1. So we have 1 times 1, and so we know that the area of that particular rectangle is 1. Okay, so I'm going to put a 1 inside the rectangle indicating its area. And we do the same thing for this other one. The area of this other rectangle is, again, the base, which is 1, multiplied by the height, and the height we said was 2, right? Because that point right there on the curve has a y coordinate of 2, and so the height being 2, so 1 times 2 is 2, and so our approximate area, which is our goal number 1, is 1 plus 2, which is 3, and that's goal number 1. So we got an approximate area between the curve and the x-axis. Okay, that's goal number 1, but goal number 2 is to interpret what it means. Okay, we'll get to what it means in a second, but the goal number 3 is knowing whether your estimate is too high or too low. Well, we have an estimate which is too low because we can see that both rectangles are completely underneath the curve, and so there's space above. The rectangles never extend above the curve, and so we have an approximation that's too low. Alright, so finally, this isn't going to really make any sense right now, but I'm going to tell you anyway that the goal number 2, interpreting what it means, when you see this symbol here, we'll get to what that symbol means later, but when you see it for right now, I want you to consider that that symbol is asking you to find the area between x equals 0 and x equals 2 of and then the function follows it, of the function, or between the function and the x-axis, x squared plus 1, and then you'll see this little dx on that. And again, I'll explain all of what that notation means, but that is what this means right now. It's an approximation for this, what we call an integral. Okay, so you'll see that over and over again. You'll become really familiar with that. It's not going to be a big deal. So goal number 1, we found an approximation, which is 3. We realized goal number 2, it's really approximating the value of this integral right here, the value of the integral. So it's approximation for that. And then we also know, again, goal number 3 is that the approximation is too low. Alright, so that's a lot of me doing stuff. That's the end of this first video, and we'll pick it up in the next video and have you do one, and we'll go from there.